All right, welcome. If you're doing higher tier GCSE Physics with AQA, then you are in exactly the right place. Today, we're going to tackle a really key topic: induced potential, transformers, and the whole national grid. Let's just jump straight in.
So let's start with a big question, one that kind of frames everything we're about to cover. Think about it. A power station can be hundreds of miles away from where you are right now, yet here you are, charging your phone. How on earth does that electrical energy travel so far and so efficiently? Well, that incredible journey is exactly what we're going to break down today. So here's our game plan. First up, we'll look at the massive problem of just moving power across a whole country. Then we get to meet the real heroes of the story: transformers. After that, we're going to go right back to basics and see how we actually make electricity in the first place, using something called the generator effect. We'll look at some real-world examples, and then, finally, we'll wrap it all up with a neat checklist of the absolute essentials you need to know for your exams.
Okay, part one, powering a nation. Before we get to the solution, we really need to understand the scale of the challenge we're facing.
So here's the core issue. Whenever you send an electric current through a wire, that wire heats up. You'll notice from the equation P equals I squared R. Now, just try to imagine sending a massive current through hundreds of miles of cable. The energy loss would be enormous. I mean, most of the energy made at the power station would literally just be lost as heat into the atmosphere before it even got to your town. It would be unbelievably inefficient, a total waste.
So how do we solve this gigantic energy loss problem? Well, this brings us to these absolutely ingenious devices that make the entire system work: transformers.
And here it is, a brilliant two-part solution. To cut down on all that wasteful heating, we need to get the current as low as we possibly can. So at the power station, they use something called a step-up transformer. This thing massively increases the potential difference. We're talking hundreds of thousands of volts. And by doing that, it crucially decreases the current. This low current, super high voltage electricity can then zip across the country super efficiently. Then, just before it gets to our homes, a step-down transformer does the exact opposite. It drops the potential difference to a much safer 230 volts for us to use, which of course brings the current back up.
But what exactly is a transformer? Well, you can see the device is actually pretty simple in principle. You've got two coils of wire, a primary and a secondary, and they're both wrapped around the same iron core. Now for your exam, you have to know this bit. An alternating current in that first, primary coil creates a constantly changing magnetic field in the iron core. This changing field then induces a potential difference in the secondary coil. It's a really fantastic bit of physics.
And the real magic is all in the numbers. This is the first key equation you absolutely must know. The ratio of the potential difference across the coils is exactly the same as the ratio of the number of turns on the coils. So, you want to step up the voltage? Simple. Just make sure the secondary coil has way more turns than the primary one. And if you want to step it down, you guessed it, the secondary coil gets fewer turns. It's simple, it's elegant, and it's incredibly powerful.
And here is your second essential equation. Now, if we imagine a perfect 100% efficient transformer, then the power you put in has to equal the power you get out. And since power is just potential difference times current, we get this relationship: Vp times Ip equals Vs times Is. This is the maths that proves why stepping up the voltage makes the current go down. Remember, get your head around these two equations and you've basically understood how transformers work.
Okay, so we know how to move electricity efficiently, but where does it even come from in the first place? Well, that brings us to our third section, the generator effect. This is the fundamental principle behind making electricity.
This idea is the absolute heart of how we generate electricity on a massive scale. It's called the generator effect, or sometimes electromagnetic induction. Basically, if you move a wire through a magnetic field or move a magnet near a wire, you generate a potential difference. It's just beautiful physics symmetry, really. Using electricity and a magnet can create movement, that's the motor effect. And, as we see here, using movement and a magnet creates electricity.
Let's break it down into 4 simple steps, just to lock it in your brain for the exam. Number 1, you need a conductor and a magnetic field. Number 2, you need movement between them. It doesn't matter if the wire moves or the magnet moves, as long as the wire is cutting through those magnetic field lines. 3, this movement induces a potential difference. And finally, number 4, if that wire is part of a complete circuit, an electric current will start to flow. That's it.
Now, this is a classic exam question. How do you make that induced potential difference bigger? Well, there are 3 main ways.
You can move the wire or the magnet faster, you can use a stronger magnet, or instead of just a single wire, you can use a coil with lots and lots of turns of wire, which is basically like using a much longer conductor. So more speed, more magnetic strength, or more wire equals more voltage. Simple.
So this whole generator effect thing isn't just some abstract concept in a textbook. It's the driving force behind technologies we use every single day. Let's have a look at a couple of key applications.
So at power stations, they use these enormous generators all based on this effect. The two types you need to know are alternators and dynamos. Now they both work by spinning a coil inside a magnetic field, but the key difference is what comes out. An alternator produces alternating current, or AC. That's where the current's direction is constantly flipping back and forth. This is what our mains electricity is. A dynamo, on the other hand, produces direct current, or DC, where the current only ever flows in one direction, kind of like the electricity you get from a battery.
And it's not just about making huge amounts of power. A moving coil microphone is another perfect example of the generator effect. When sound waves hit the microphone, they make a tiny coil of wire vibrate back and forth inside a magnetic field. And what happens when you move a coil in a magnetic field? It induces a current. The pattern of this new electrical signal perfectly matches the pattern of the original sound waves. You are literally turning sound into electricity. How cool is that?
Right, let's pull all of this together. As we said right at the start, this whole topic is for higher tier students only. So if that's you, these next points are your absolute essential revision checklist. Pay attention to this bit.
Okay, quick recap. Make sure you have these 4 areas totally sorted. First, can you explain the generator effect in your own words? Second, can you clearly describe the job of a step-up and a step-down transformer? Third, are you confident using both of those transformer equations? And finally, can you explain the applications we've talked about, alternators, dynamos, and microphones? If you can honestly tick all those boxes, you're in really great shape for the exam.
And we'll finish up with a little thought to take away with you. We've seen today how the generator effect turns motion into an electrical signal. But what about the motor effect, which you've probably studied already? That does the opposite. It turns electricity back into motion. So how does an electric car use that exact opposite principle to turn the chemical energy stored in its battery into the kinetic energy that makes its wheels spin? Have a think about it. It's the perfect way to connect the dots in your physics knowledge.